Um, Thank you, everyone, to give me this opportunity to present my research, and also thank you to the organizers for making some adjustments in the schedule, as I was not able to be here this morning. So in this talk, I'm going to be discussing something a little bit outside the norm that's usually talked about with neuromorphic computing. And I'm going to be discussing problems related to network analysis and network dynamics. And these are problems that have a lot of real-world applications, mostly in terms of when do small bad things turn into very large bad things. So you could be concerned with how fast will a disease spread through a social network, if you have a power outage in one part of a power grid, is that going to cascade into a large-scale blackout? Or in terms of the Dyn attack of 2016, how many baby monitors does it take to take down the internet? And of interest is understanding the structure underlying a given network. So if you consider a network just as a graph of vertices and edges, there's a lot of interesting questions to be answered. What is the shortest path between two vertices? Or what could be considered important vertex on a graph, and how do you quantify that? And actually the focus of this talk is how do you identify groups of vertices in a graph that are considered strongly related or strongly connected. So what we're using neuromorphic hardware for is to generate some spiking data that we're going to incorporate into some well-known algorithms for community detection. And our goal is we want to take some graph, extract very minimal amount of data from that graph, very little information from that graph, and use that information to build some spiking neural network. And in particular, we are avoiding large-scale training, and our spiking neural networks are built using deterministic neurons, and our synapses are all static. So just a quick overview of the problem of community detection. In a undirected, unweighted graph, how can you extract information from this graph that'll tell you what vertices are more closely related or more strongly connected to each other than to the rest of the graph? And this is an example of one of the graphs that we're going to be analyzing in this talk. And I acknowledge that real-world networks are extremely large. What I present here in this talk are very preliminary proof-of-concept results, and we're going to focus on these small benchmark graphs of 128 vertices. And these are generated with some known set of community labels and memberships. And again, as I mentioned, what we are going to do is we're going to build a method for analyzing the graph structure of these undirected, unweighted graphs that incorporate spiking data. So the three main areas that we're concerned with is just how can we construct spiking neural networks for this task? What characteristics are needed? What is useful output? How can you analyze spiking data and incorporate that into some well-known community detection methods? So where this all began for us is the Hopfield neural network. And this is a recurrent neural network that can be used for graph bipartitioning. And what was very attractive to us about Hopfield networks was constructing a Hopfield network for the task of graph bipartitioning. It's demonstrated in this small cartoon in the right-hand side here. You would take some graph that you want to divide into two equal partitions, map it to a recurrent neural network, and then through asynchronous updating of the neural states, eventually this will converge to a steady state where all the neurons in one community are in the state labeled +1, and all the neurons in another partition have the opposite label of -1. But the determination of the edge weights used to construct this neural network can just be determined by the adjacency matrix of your graph and some parameter mu. And by tuning mu, that's going to affect how efficient this network is at bipartitioning some given graph. So this is really what we wanted to exploit when we were building our spiking neural networks. We just want to take some graph, and you know where the edges are, and we want to use that to just immediately define synaptic weights for a spiking neuron system. The challenge is we need to identify some heuristics for setting the synapse weights and the various parameters associated with our spiking neuron model. And also, in this Hopfield network demonstration, the bipartitioning converges to this steady state where neurons in partition 1 are all in the +1 state, and neurons in partition 2 are all in the -1 state. How do we get that behavior mapped into the spiking neuron behavior? And what we finally settled on is that neurons in the same community, we want them to exhibit some sort of localized spiking behavior. So if one neuron in a community fires spikes, we want other neurons within the same community to fire spikes, not quite synchronously, but very close in the same, in a short time frame thereafter. So the neuron model that we choose to build our spiking neural networks, I'm going to skim over this very briefly. It's just leaky, integrate, and fire neuron models. And the state of the neuron is going to be dependent on some external current, either from an applied stimulus, like some driving current, or it can be affected by the arrival of spikes from other neurons. And so, again, following that basic demonstration of a Hopfield neural network, here is how we've been constructing our initial attempt for spiking neural networks for community detection. And right now, for the results I'm going to show in the following slides, these are just simulated using the Python library Brian 2. And so what we're going to do is take some undirected graph that we wish to analyze the community structure, map that graph to first a set of spiking neurons connected by positively weighted synapses. So all the vertices of our graph get mapped to leaky, integrate, and fire neurons, and these neurons have all the same parameters. They're homogeneous. The edges that exist on our graph are mapped to positively weighted synapses. And then to complete our model, any absent edges from our original graph are then added to our spiking neural network as negatively weighted synapses. So this is mapping some graph to a fully connected system of spiking neurons. And as I mentioned, the neurons are all homogeneous. They have the same firing threshold. They have the same time constant tau. They have the same reset voltage, et cetera, et cetera. And the synapses themselves, the positive synapses and the negative synapses have the same amplitude, just different sign. So once we have constructed our spiking neural network, now we need to figure out how to generate some spiking output and then extract information from that output. So to generate spiking output, what we choose is that we want to drive individual neurons, and we want to be able to identify who is spiking in response to a driven neuron. So for every neuron in our spiking neural network, we apply some square pulse external current to it. And up in this upper right-hand corner, this is just a small cartoon of how you would drive a set of 4 neurons. You would just apply 4 identical square pulses, just spaced apart in time. And the motivation for using square pulses is that it effectively you are just driving each neuron with some constant external current. And when a neuron is being actively driven, it's going to fire at some uniform firing rate. And then what the result of this is that the spiking dynamics are greatly simplified. A neuron is firing either because it is being actively driven, or a neuron is firing because multiple spikes are arriving from some driven neuron, and it is spiking in response. And a third possible behavior is that two neurons that are connected by a negatively weighted synapse, if one neuron is being driven, it's going to actively suppress the second neuron from driving. So I mentioned what we are trying to generate is a localized response from small groups of neurons. So of the various neuron parameters that you can use to define a leaky integrate and fire neuron, it's the threshold, the synaptic weight, and the time constant tau. We choose these such that when you drive one neuron, it only causes a small subset of neurons to fire in response. These are the nearest neighbors, and it's possible to get additional neurons to fire based on the density of connections in your graph. But the spike raster that you can generate from these systems, again, this result here was just generated using Brian 2. The darker lines show the response of a driven neuron, and it's going to cause some small subset of neurons to fire in response. So once we have generated the spike response from a fixed set of neurons for some particular graph, we then decode this just by converting every spike train into a binary vector. So each binary vector is just built by defining some time bin width delta t, and the entries of the binary vector are just 1 or 0, depending on whether or not a spike occurs during a given time window delta t. And what we are going to do is then compare the binary vectors generated from an entire system of spiking neurons, and and neurons that have similar spiking behavior we're going to identify as being contained in the same community. And we define this similarity just using a Hamming metric, Hamming distance metric, where this lowercase h takes in two binary vectors, xi and xj, and just measures the Hamming distance between them. Capital N is the length of the binary vectors themselves. And so this spike train similarity will reach 1 if two binary vectors are identical. In the case that you are comparing some spike train, say xi, to the spike train of a neuron that does not fire at all, so if xj is just an all 0 vector, in that case we just define the similarity to be 0. So applying this concept to one of these benchmark graphs on 128 vertices, we just set up a small test, map this graph to a fully connected spiking neuron system, drive each neuron in a random order, drive every neuron in the graph, and then if you just build a comparison matrix of the decoded binary vectors, you can see that there is marked similarity between neurons in the same communities. And community 1 is clearly distinguishable from 2, 3, and 4, and likewise for all 4 communities. Neurons within the same community will have a higher degree of similarity than between neurons in different communities. And again, this is dependent on the width of this time step that you choose to decode the spike trains themselves. Okay. And again, just reiterating that single communities can be discerned from the remainder of the communities. This Hamming metric is linearly separable depending on choosing an appropriate time window, delta t, and it also is dependent on the number of neurons that you drive within the whole system. So if I just began with the initial graph of 128 vertices, mapped it to a fully connected spiking neuron system, but only chose to drive some random subset of neurons that covered only 25% of the original graph, I wouldn't get a measure of similarity or distinguishability between the 4 different communities. But if I drove more and more neurons in the system, it becomes much clearer how to distinguish one community from the remaining 3. And so this linear separation of the Hamming metric led us to incorporate or consider incorporating spiking data into a well-known community detection algorithm known as label propagation. So for non-spiking implementation of label propagation, you begin with some graph. Each vertex in your graph is initialized with a unique label. And you go through the graph and you update the label of each vertex such that the label of a given vertex is going to attempt to agree with the majority of its immediate neighbors. And eventually this will converge to a final label set, and from that final label set you will identify communities based on just regions of consensus. And so the spiking implementation, again, you go through and you build this fully connected spiking neuron system, drive all the neurons by a square pulse, generate your spike raster, decode the information, and from this set of now decoded spike trains, we now implement this sort of spiking label propagation. But now what you do is you just choose a neuron, you fix its label, and then you apply that label to any neuron that has some measure of similarity in their spike train responses or their spiking responses. Any neuron that is similar to your first neuron, X0, you apply its label to that set of neurons. So let's see. So then with this spiking label propagation approach in hand, what we did is we looked at a small set of benchmark graphs on 128 vertices with varying community distributions. And again, these are all generated with known memberships and known labels. So we start with our first graph instance had 16 communities of 8 vertices each, and it went all the way up to the fully connected graph on 128 vertices just as a to act as a control. So in the spiking label propagation, again, you initialize every neuron with a unique label, and you go through and you just allow the label of each neuron to affect some small subset of neurons that are considered similar. And eventually, after you update the label of every single neuron in your system, you will end up with some final label set. And it is possible to have many trivial solutions. One, you just wind up with a single label, and the other trivial solution is where you don't deviate from your original label set at all. But for some graphs, for some choice of the similarity threshold, it is possible to get a final label set between these 2 trivial solutions. And based on the variance of information, we observed that it does correspond to the ground truth label set. Actually getting this onto hardware, we don't want to embed a fully connected system. So instead, we choose to replace our fully connected spiking neuron network with just a set of sparse trees. And just this simplifies our neuron model that we use. Basically, we just replace each neuron, well, we just embed a single neuron and its immediate neighbors, and we just feed in some discrete set of spikes, and the output will just be the same set of spikes, and the response from its immediate neighbors will be at a lower firing rate. Excuse me. And under this sparse embedding, what we find is that you do lose some detail in the spike raster that you generate. But the good news is that so far we have not seen significant effects on the linear separability of the Hamming metric. If we apply it to the same set of benchmark graphs on 128 vertices, we get very similar results to the fully connected model. And also, if you compare the results of the spiking label propagation using a model deployed on neuromorphic hardware to the fully connected model simulated in Python, you see similar behavior where the label set can either converge to one of two trivial solutions or to a non-trivial solution. And so this general approach to community analysis of undimensioned graphs, we first have a fully connected model that can be mapped to a sparse embedding for neuromorphic hardware. And the benefits of the neuromorphic hardware is it can generate this spiking data very, very quickly. So just in general, these are just general proof of concept results using homogeneous neurons, static synapses, and a very small set of benchmark graphs. For future work, we would like to start incorporating more heterogeneous systems, such as plasticity in the synapses or heterogeneous neurons. And also for the label propagation, we would like to incorporate some early stopping so you don't have to update the label of every neuron in the system itself. Additionally, we would like to investigate where's the resolution limit for this approach. What is the smallest community you could actually detect in a large graph? And with that, I'm going to close with the sincere thanks to Brian Van Essen at Livermore for allowing us access to his True North system, and also members of his research group that have helped me get set up on the system itself.